The Boötes Void sits within a much larger pattern that fills the observable universe. On the widest maps, galaxies do not appear spread evenly. They gather into chains and sheets with knots where clusters form, and with long stretches where far fewer galaxies are found. This arrangement is often called the cosmic web. It emerges from gravity acting over billions of years on matter that begins with small differences in density. The densest parts pull in more material and become richer in galaxies. The least dense parts lose material to their surroundings and become emptier with time. A cosmic void is one of these underdense regions. It is not a hole cut out of space, and it is not truly empty. It is a volume where the average amount of matter is much lower than in the surrounding web. The Boötes Void is an example that becomes well known because of its scale and its position in the sky. It lies in the direction of the constellation Boötes, and it is described as a very large region where surveys find far fewer galaxies than expected for a similar volume elsewhere. When astronomers speak of the void in simple terms, they mean a broad three-dimensional region defined by distance and by direction, where the usual crowd of galaxies thins to a sparse scattering. On a map that includes nearby clusters and filaments, the void appears as a wide clearing among the brighter structures that frame it. The first step in understanding any claim about something inside a void is to hold the scale in mind. The Boötes Void is not a small gap between neighbouring galaxies. It spans a volume large enough that light takes hundreds of millions of years to cross it. In that span, the normal cosmic web would contain many galaxies, including bright ones that stand out. In a void of this size, surveys still find some galaxies, but the density is low, and those galaxies tend to be smaller, fainter, and more spread out. The phrase that a void is empty can be useful as a first picture, but it can also mislead. Even where galaxies are rare, there can still be gas-dark matter, and a thin population of stars bound inside faint galaxies. There is also the background radiation that fills all space, and there are particles that travel through intergalactic regions. What changes in a void is the concentration of matter and the number of luminous systems that mark where matter gathers. The Boötes Void therefore belongs to a family of structures that are understood as natural outcomes of cosmic evolution. Yet its apparent emptiness, when first revealed by large surveys, seems stark. It draws attention because it asks a quiet question about what is typical and what is unusual in the cosmic web. In the outer frame of the topic, the void is part of a statistical landscape. Astronomers do not assign it meaning by how it feels, but by how it compares with expectations drawn from other regions. A survey measures the positions and distances of galaxies. When a region stands out as having far fewer galaxies over a large span, it becomes a candidate void. The Boötes Void is then described by its approximate direction, by its approximate distance range, and by an estimated size. Those estimates can shift as surveys improve and as more galaxies are found. The outermost view is therefore not a fixed object with a sharp wall. It is a large underdense region whose boundaries depend on the depth and completeness of the data. At this wide level, one can imagine standing far from the web and looking at it as a whole. Dense filaments form a loose scaffold, while voids form the spaces between. The Boötes Void is one such space, and its size places it among the larger known voids in the nearby universe. The word nearby here does not mean close in everyday terms. It means within a range where galaxy surveys can measure many distances with good precision, and where the void can be mapped with enough galaxies around it to give it a shape. When a void is discussed, it is also important to remember how distance is understood. Astronomers often use redshift, a stretching of light waves that grows as the universe expands as a proxy for distance at large scales. They also use other distance methods when possible. For the widest mapping, the important point is that the void is a three-dimensional region, not a flat patch on the sky. If a detection is said to be inside the Boötes Void, that means the signal is placed at a distance range that overlaps the void's mapped volume and at a direction that points through that volume. The placement depends on how well the distance is known for the source, and how the void's boundaries are defined. A second outer fact is that the emptiness of a void is measured relative to average cosmic density. The universe has a mean density of matter, including ordinary matter and dark matter. In dense regions, the matter density rises above the mean. In voids, it falls below the mean. The Boötes Void is considered strongly underdense, which means the deficit is large. In a practical sense, it means that within the defined volume, the count of galaxies brighter than a certain limit is much lower than the count expected from the average. But this depends on the limit. If a survey can only detect bright galaxies, it may define a void that looks emptier than it truly is, because faint galaxies remain unseen. As surveys go deeper, some of those faint galaxies appear, and the picture refines. Even then, the region can still be underdense. The void remains real in the statistical sense even if it is not perfectly empty. The cosmic web picture is supported by observations and by simulations. In simulations that follow matter under gravity with the expansion of the universe, included voids emerge naturally. Their sizes and shapes depend on cosmological parameters and on the distribution of matter at early times. Large voids are rarer than small ones, but they are not forbidden. The Boötes Void in this outer framing is therefore not a contradiction. It is an example of an extreme but possible region in the distribution of matter. The phrase that something is detected inside it becomes intriguing only when the claimed detection seems to clash with what is typical for such a low-density environment. Yet at this stage, the correct stance is patient. A void is a region of low galaxy density, not a region where nothing can exist. What can exist there tends to be subtle, faint and difficult to measure. The outermost layer is also shaped by the way humans collect data. Surveys cover the sky in patches. They have selection effects, meaning they preferentially include certain kinds of galaxies and miss others. They are limited by dust in the Milky Way, by the brightness of stars, by instrument sensitivity, and by time. The Boötes Void is mapped through these methods, so the first layer of understanding includes the observational context itself. A claim about an unexpected detection inside a void often begins as a pattern in data. It can be a faint population of galaxies, a signal seen in radio, an imprint in the background light, or a statistical anomaly in how matter seems distributed. In the widest view before any particular claim is examined, the setting is a vast underdense region in the cosmic web defined through galaxy counts and distances, and refined over time as data improves. The Boötes Void is one of the most prominent examples of such a region in the sky, and it offers a quiet stage where the usual bright markers of structure are scarce. The first region is therefore a map of absence rather than presence, but it is still a physical region filled with space-time radiation and the thin remaining matter that gravity has not gathered into denser forms. A region like the Boötes Void is identified through evidence, not through a single image. The evidence comes from measurements that link points of light to positions in three-dimensional space. Astronomers begin with a wide survey of the sky and record objects that look like galaxies. Each object has a brightness, a colour and a shape that can be measured. But the key step for a map of a void is distance. Distance allows a sky pattern to become a volume. In modern work, distance is often inferred from redshift, the stretching of light to longer wavelengths as the universe expands. When a galaxy's spectrum is measured, the shift of known spectral features gives a redshift value. Under standard cosmology, that redshift corresponds to an approximate distance and a look-back time, meaning how long the light has been travelling. In a survey map, a void appears when a large volume shows a strong deficit of galaxies over a defined redshift range and direction. The first point is therefore that the void is not a gap that someone sees directly, but a statistical feature built from many galaxy measurements. The process begins with selection. A survey has a brightness limit because instruments can only detect objects down to a certain faintness within a given exposure time. If the limit is bright, only the more luminous galaxies are included. If the limit is deeper, many more galaxies appear, including smaller and fainter ones. Because of this void, boundaries depend on the survey depth. A region that looks nearly empty in a shallow survey may contain a modest population of faint galaxies that become visible later. Even so, a true void remains underdense compared with other regions at the same distance. The next step is defining a reference. To say that a region is underdense, astronomers compare the number of galaxies in a chosen volume to the average number expected. The average can come from the same survey using large volumes to estimate typical density, or from models that predict galaxy counts for a given cosmology and selection. The comparison requires careful accounting for survey geometry. The sky coverage may be incomplete. Some directions are blocked by the Milky Way's dust and stars. Some parts have poorer data quality. The survey may not include all galaxies equally at all distances because faint galaxies are easier to miss farther away. Astronomers correct for these effects with completeness models, and they test the robustness of void identification by varying selection and checking whether the same void-like region persists. In practice, void-finding algorithms use the positions of galaxies to locate large empty spheres or connected low-density regions. Some methods place spheres in the galaxy distribution and look for the largest ones that contain few or no galaxies above the survey limit. Other methods reconstruct a smooth density field from the discrete galaxy points and then identify the connected underdense regions. The Boötes Void gains its name and prominence because early surveys in that direction reported a large region with unusually few bright galaxies. Later deeper surveys find more galaxies within it, but still confirm that the density remains low compared with surrounding filaments. This leads to a second point about what it means for something to be inside the void. The phrase suggests a neat interior, but the definition of inside depends on how a boundary is drawn. A boundary can be defined by a chosen density threshold, such as the region where galaxy density falls below a certain fraction of the mean. It can also be defined by the extent of the largest empty spheres found by an algorithm. Different choices yield slightly different shapes and sizes. Real voids are not perfect spheres. They can be elongated, merged with neighbouring underdense regions, and bounded by complex filaments. Therefore, when a detection is assigned to the Boötes Void, the assignment should be understood as probabilistic and method-dependent unless the source has a well-measured distance and lies well within the low-density region, under multiple definitions. Distance measurement itself has layers of uncertainty. Spectroscopic redshifts derived from detailed spectra can be precise. Photometric redshifts estimated from broad band colours without a spectrum are less precise and can scatter objects forward or backward in distance. For a claim of something inside a void, the reliability of the distance matters. A source that seems to sit in the void using a photometric estimate might with a spectrum move to the void's edge or beyond it. This is not an error in the sense of a mistake. It is the normal consequence of measurement limits. A third layer comes from projection. The sky is a two-dimensional projection of a three-dimensional universe. A line of sight toward Boötes passes through many distances. A bright or unusual object seen in that direction might not be at the void's distance. It could be closer within the Milky Way. It could be farther behind the void. For galaxies, distance sorting helps separate these layers, but for some kinds of signals the separation is harder. A patch of radio emission, for example, might be associated with a nearby galaxy, a distant galaxy, or even with a diffuse source, and its distance may not be immediately known. The term detected therefore needs to be linked to a specific measurement and a specific distance inference before it can be said to be inside the void in a strong sense. Another important aspect of void identification is bias. Galaxies are not perfect traces of mass. The distribution of galaxies reflects the distribution of dark matter, but not one-to-one. In low-density regions, small changes in conditions can affect whether a galaxy forms and how bright it becomes. Therefore, a galaxy-defined void may not correspond exactly to a mass-defined void. Some methods use weak gravitational lensing, the subtle distortion of background galaxy shapes by foreground mass to infer mass deficits. Others use the motions of galaxies, since galaxies tend to flow out of underdense regions and into denser ones, leaving characteristic velocity patterns. These methods can support the interpretation that a region is genuinely underdense in mass, not just underpopulated in bright galaxies. Yet each method has its own noise and systematic uncertainties. In the outer mapping context, the Boötes Void is best understood as a large underdense volume, identified primarily through galaxy surveys and refined by later work. It exists as a region where the probability of encountering a galaxy above a given brightness is significantly lower than average. The word void can suggest an absence of structure, but even within voids there can be delicate structure. Faint galaxies can line thin filaments. Small groups can exist. Gas can collect in wisps and sheets too thin to shine strongly. So the act of identifying the void already depends on the chosen tracer and the chosen threshold. This is why any later claim about an unexpected detection inside it must be paired from the start with an explanation of how inside is defined. Without that, the claim floats without anchor. When the mapping is done carefully, however, the void becomes a useful laboratory. Because it is underdense, it provides a contrasting environment to clusters and filaments. It allows astronomers to study how galaxies form when external influences are weaker, how gas behaves when it is not crowded, and how the cosmic web's empty regions evolve. Within this outer region of understanding, the main task is clear. Define the Boötes Void as a measured underdensity. Define the method that draws its boundaries, and define the distance framework that places any object or signal within that volume. Only then can the meaning of a reported detection begin to be evaluated with calm precision, without forcing it to sound more puzzling than the data requires. When a report says that something is detected inside the Boötes Void, the word detected can hide several different kinds of evidence. In astronomy, detection rarely means a direct encounter. It usually means that instruments record a signal that stands above background noise in a way that can be measured and repeated. The signal might be light, meaning electromagnetic radiation, or it might be a pattern in how light from other objects is altered. It might be a statistical excess or deficit in a survey map. It might be a motion pattern inferred from redshifts. The first step is to separate the types of detection, because each type carries a different level of certainty about location, physical size, and physical nature. The most familiar detections are images and spectra of galaxies. A galaxy can be detected as a patch of light in optical or infrared images. If the galaxy is bright enough, a spectrum can be taken and the redshift can be measured. In that case, the object's position in the sky and its approximate distance are both known, and it can be placed within or outside the void with relatively strong confidence. Even then, the confidence depends on the precision of the redshift and on how the void boundary is defined, but the object is at least tied to a three-dimensional position. Another common type of detection is diffuse emission. This can appear as a faint glow spread over a region, rather than as a compact object. Diffuse emission can come from gas that is heated and radiating from dust, scattering light from synchrotron radiation, produced by fast electrons spiraling in magnetic fields, or from a blend of many faint sources that cannot be resolved individually. Diffuse signals can be real, but they are harder to interpret because they are sensitive to how background is removed and how foreground contamination is handled. For a diffuse detection to be confidently placed inside a void, it must be linked to a distance. That link can come from association with known galaxies at the void distance from spectral lines, whose redshift can be measured or from other methods. Without such a link, a diffuse patch seen toward the void might actually lie closer or farther along the same line of sight. A third category is absorption. Sometimes the signal is not extra light but missing light at specific wavelengths. If a bright background source lies behind thin gas, the gas can absorb certain wavelengths and leave lines in the background spectrum. The most common example is absorption by hydrogen gas, which can leave a characteristic line in the ultraviolet. Other elements leave their own patterns. Absorption detections can reveal gas that would be too faint to see in emission. They can also provide redshift information, because the absorption lines are shifted by the expansion of the universe. In principle, absorption can show that there is gas at a given distance along the line of sight, even if there are few galaxies nearby. But absorption requires a suitable background source like a quasar, and it samples only a narrow pencil beam. It does not automatically describe the wider volume. In the context of a void, absorption lines can reveal that some gas remains in underdense regions, and they can help measure its composition and temperature. Yet a single absorption detection does not mean the void is filled with unusual matter. It means that along one path matter is present at a measurable level. A fourth category is gravitational lensing. Mass bends light, and even when the bending is weak, it can slightly distort the shapes of many background galaxies. By averaging these distortions, astronomers can map mass statistically. A void can appear as a negative lensing signal consistent with a mass deficit. But lensing can also be used in reverse. If a report suggests there is an unexpected mass concentration inside a void, it might come from lensing signals that imply more mass than expected in a region otherwise mapped as underdense in galaxies. This kind of detection is subtle. Weak lensing measurements require careful control of systematic errors such as distortions introduced by the telescope and the atmosphere for ground-based observations. They also depend on accurate distance estimates for the background galaxies. A lensing-based claim about something inside the void therefore rests on careful statistical work and independent checks. Another detection mode is radio mapping of neutral hydrogen. Hydrogen atoms can emit radio waves at a specific wavelength when the spin state of the electron flips. This emission is weak, but large radio telescopes can detect it from gas in galaxies, and in some cases from more diffuse structures. Neutral hydrogen detections are especially useful because they can provide redshift information through the shift of the radio line, allowing three-dimensional placement. In a void, radio detections can reveal gas-rich faint galaxies that are hard to see in optical light. Such galaxies can exist in underdense environments. If a report of a detection inside the Boötes Void involves neutral hydrogen, it might reflect the discovery of void galaxies rather than something physically incompatible with a low-density region. Yet the word makes no sense could still appear in a headline because the scale feels surprising. At the level of physics, the question is whether the detected signal is truly unexpected under consensus models, or whether it is unexpected only relative to a simplified picture of emptiness. A further category is high-energy emissions such as X-rays. Hot gas emits X-rays, as do the environments around actively feeding black holes. If an X-ray source is claimed inside a void, the likely candidates include an active galaxy, a cluster of galaxies, or a background source seen through the void. Because voids have fewer galaxies, they also have fewer massive clusters, so a strong cluster like X-ray glow at the void distance would be unusual. But again, distance is decisive. Many X-ray sources are compact and can be matched to optical counterparts, whose redshifts are measured. Without that, a source might be placed incorrectly. Detection language can also refer to statistical anomalies. For example, a survey might find a region where the cosmic microwave background shows a slightly different temperature pattern than average, and someone might connect that to a void. The cosmic microwave background is the remnant radiation from the early universe, and it has tiny fluctuations in temperature, Large structures in the later universe can slightly alter this background through effects tied to the expansion of space and the presence of matter. These effects are small and hard to measure. A claim that something is detected inside a void based on such patterns often involves statistics and careful control of bias. It can also be sensitive to how the region is selected. If a report uses detected to mean a correlation rather than an object, the evaluation must focus on the strength of the correlation and the possibility of chance alignment. The key point in this region is that detection is a technical word that should always be followed by a description of the measurement, the signal to noise, and the method used to infer distance. Without distance inside, the void remains a statement about direction rather than location. Even with distance, the nature of the detection matters. A compact galaxy with a spectroscopic redshift is a straightforward detection. A diffuse glow without redshift is not. An absorption line can be strong evidence for gas along a narrow path, but it does not map the whole region. A lensing signal can suggest mass distribution, but it is statistical. Each type is valid in its own way, but none justifies an immediate leap to contradiction. In calm terms, a detection inside the Boötes Void can mean one of several things, ranging from the discovery of faint galaxies within a known underdense region to the identification of diffuse gas through absorption, to a subtle statistical signal linked to mass or background radiation. The next step after naming the detection mode is to trace how the signal travels through space to the instrument and how it is separated from other contributions along the same line of sight. That step remains in the outer region, because it still deals with signals and measurements rather than with the internal physical processes of the detected source. Light is the main messenger across cosmic distances, and the path it takes to reach a telescope shapes what can be claimed about a detection inside a void. Light here means all electromagnetic radiation from long-wavelength radio waves to short-wavelength X-rays and gamma rays. Each band interacts with matter differently, and each band faces different obstacles along the line of sight. When a signal is seen toward the Boötes Void, the first calm question is whether the signal truly comes from within the void's distance range, or whether it is simply aligned with that direction. The line of sight passes through many layers of matter, from the Earth's atmosphere for ground-based telescopes to dust and gas in the Milky Way to the intergalactic medium between galaxies, and then onto the distant universe behind the void. A detection can be altered by any of these layers, and some layers can produce signals of their own. The light that reaches a detector is therefore a sum of contributions plus the noise of the instrument. Astronomers separate these contributions through careful calibration and by comparing multiple observations. The process is disciplined, but it is never perfect, so uncertainty is part of the result. One of the simplest complications is foreground contamination from the Milky Way. The Milky Way contains dust that absorbs and scatters visible light. This dust is not spread evenly across the sky. In some directions it is thin, and in others it is thick. A region can appear to have fewer galaxies in a shallow optical survey, partly because dust hides faint galaxies. Modern surveys correct for this by mapping dust and adjusting for extinction, meaning the dimming and reddening of light. Yet these corrections have limits. If a void's direction lies in a relatively clean part of the sky, dust is less of a concern, but it is never absent. In radio, the Milky Way emits strongly through synchrotron radiation and through emission from gas. In infrared, the Milky Way's dust glows. In X-rays, the Milky Way contributes hot gas emission. Each of these foregrounds can mask or mimic faint extragalactic signals if not handled carefully. For a detection that claims something surprising inside a void, the burden is to show that the signal is not a foreground artifact. Beyond the Milky Way, the line of sight includes other galaxies that are not part of the void. A distant galaxy behind the void can be seen through it, and if its distance is not measured, it might be mistakenly associated with the void. This is especially likely for faint unresolved sources where only an image detection exists. A faint smudge in an optical image could be a small galaxy at the void distance, or a much larger galaxy far behind it, whose light has been stretched and dimmed by distance. Spectroscopy can resolve this by measuring redshift, but spectroscopy is costly and not always available for very faint sources. Photometric redshifts help, but they can misplace some sources, particularly when the galaxy's colours are affected by dust, by strong emission lines, or by limited filter coverage. Therefore, the path from image to distance is one of the key steps that can turn an ordinary background object into an apparent inhabitant of the void. Another layer is the intergalactic medium, the thin gas that fills the space between galaxies. Even in void, some intergalactic gas remains. This gas is mostly hydrogen and helium with traces of heavier elements. In many directions, it is too thin to emit much light, but it can leave absorption features in the spectra of background sources. These absorption features are important because they can reveal gas where no galaxies are visible. Yet they also complicate interpretation because they show that the line of sight crosses gas at multiple distances. A spectrum of a quasar behind the void can contain many absorption lines from intervening gas clouds at different redshifts. Some of those lines could correspond to gas within the void region, but others might correspond to gas in filaments and galaxy halos outside it. Sorting them requires careful matching of redshifts and ideally knowledge of nearby galaxies that might host the gas. In a void direction, the matching can be harder because there are fewer obvious galaxies to associate with the absorption. That does not mean the absorption is meaningless. It means the geometry is more open, and the same absorption line can have multiple plausible physical settings. Light can also be altered by scattering. Dust grains scatter shorter wavelength light more efficiently than longer wavelength light, which can change the apparent colour of sources and affect photometric distance estimates. In the intergalactic medium, scattering is generally weak, but within galaxies and their halos, dust can be significant. A background source seen through the outskirts of a foreground galaxy might be dimmed and reddened, and if the foreground galaxy is not recognised, the background source could be misclassified. This effect can matter for rare faint detections where the classification rests on subtle colour differences. Another way the path matters is through the instrument's response. Telescopes do not record the sky directly. They record a convolution of the sky with the instrument's point spread function plus noise. For extended diffuse signals, background subtraction becomes critical. Astronomers must estimate the baseline level of emission and remove it to isolate the source. If the baseline varies across the field, or if there are faint unresolved sources everywhere, the subtraction can leave residual patterns that look like diffuse structure. This is a common challenge in studies that search for low surface brightness features. A void direction might be chosen because it is relatively clean of bright galaxies, which helps reduce confusion, but it can also mean that the signals sought are extremely faint and close to the instrument's limits. In such cases, small calibration errors can have large effects. A claim that makes no sense often begins at this edge of detectability, where repeated checks are needed to confirm that the signal persists across instruments observing runs and analysis methods. The travel of light across cosmic distances also includes cosmological effects. As the universe expands, light waves stretch, shifting to longer wavelengths. This redshift changes where features appear in different bands. It also dims surface brightness in a way that grows strongly with redshift. A distant galaxy can therefore look faint and diffuse, even if it is intrinsically bright. In a direction that includes a void at moderate distance, there can still be very distant galaxies behind it, whose light is stretched into infrared bands. If observations are taken in one band, some sources might be missed or mischaracterized. Multi-wavelength observations help, but they require coordination and careful matching of resolutions and sensitivities. The outer lesson is that the path of light is long and layered, and each layer adds ambiguity unless distance is measured directly. When a detection is said to be inside the Boötes Void, the claim becomes stronger if the source has a spectroscopic redshift, placing it within the void's redshift range, and if its position is well within void boundaries under multiple definitions. The claim becomes weaker if the source lacks a secure distance, or if the signal is diffuse and could be shaped by foregrounds or instrument effects. This does not dismiss the detection. It frames the work required to interpret it. In calm scientific practice, the next inward step is to treat the light not only as a carrier of location, but also as a carrier of physical conditions, because different wavelengths reveal different processes. Yet before that inward step, the outer region must be settled. What is seen in what band, with what confidence, and with what evidence that the signal's origin is truly within the underdense volume, rather than somewhere along the same line of sight. The outer conditions of a large cosmic void can be described in terms of what is present on average, even when the details vary from place to place. The Boötes Void is underdense in galaxies, and by implication underdense in matter compared with the cosmic mean. This shapes the environment in several connected ways: how much gas is available, how strong typical gravitational pulls are, how often galaxies interact, and how energy from stars and black holes is injected into surrounding space. In a dense cluster, galaxies are close together, hot gas fills the cluster, and interactions are frequent. In a void, galaxies are far apart, and the space between them is dominated by very thin gas and by dark matter distributed more smoothly. The first description of void conditions begins with density. Matter density in a void is lower than average, but not zero. The dominant form of matter in the universe is dark matter, which does not emit light but exerts gravity. Ordinary matter made of atoms is a smaller fraction. In voids, both components are reduced relative to the mean, though the exact ratio can vary. The reduction in density means the gravitational potential wells are shallower. There are fewer deep wells where large galaxies and clusters form. As a result, the typical galaxies that do form in voids are often lower in mass and lower in luminosity than galaxies in denser regions, though there are exceptions. The low density also means that the intergalactic medium in a void is thinner. The intergalactic medium is mostly ionized hydrogen and helium, meaning the atoms are split into nuclei and electrons. This ionization is maintained by ultraviolet light from galaxies and quasars, and by the thermal history of the gas. In the wider universe, much of the intergalactic medium is warm, with temperatures that can range from tens of thousands of degrees to much higher in shock-heated regions near filaments. In voids, the gas tends to be cooler and less shocked, because there are fewer strong gravitational collapses to heat it, though it is still typically ionized. Because the gas is thin, it does not radiate strongly in most bands. It is instead detected indirectly, often through absorption lines in the spectra of background sources. That indirect detection is one reason void conditions are discussed with caution. The measurements sample limited lines of sight and require interpretation. Another baseline condition is radiation. The cosmic microwave background fills all space with a nearly uniform glow at microwave wavelengths. It sets a faint bath of photons that is present in voids as in clusters. There is also an extragalactic background light from the accumulated starlight and dust emission of galaxies across cosmic time. In a void, the local contribution from nearby galaxies is smaller because galaxies are rarer. That can affect the local ultraviolet background, which influences the ionization state of gas. Yet the background is not created only locally. Light from distant galaxies and quasars travels through space, so the ultraviolet field in a void is still shaped by sources far away, though it may be somewhat reduced compared with regions near many galaxies. The void's low density also affects magnetic fields and cosmic rays, though these are harder to measure in the intergalactic medium. Magnetic fields exist in galaxies and in the gas between galaxies, but their strength and structure in voids remain uncertain. Some constraints come from studies of high-energy gamma rays, and from radio observations of diffuse emission. The uncertainty here is substantial because signals are faint and analyses can be model-dependent. What is known is that void environments are not expected to host strong, widespread synchrotron emission unless there are mechanisms to accelerate particles and maintain magnetic fields across large volumes. Therefore, a reported diffuse radio signal inside a void can sound surprising, but the evaluation depends on whether the emission is truly spread through the void or instead associated with discrete sources or with structures on the void's boundary. Temperature and pressure in the intergalactic medium are also part of the outer conditions. In everyday terms, temperature in such thin gas refers to the average kinetic energy of particles, not to a sensation of warmth. Pressure depends on both density and temperature. In voids, density is low, so pressure is low even if the gas is ionized and not extremely cold. Low pressure means that gas is less confined. It can expand and flow. Over cosmic time, matter tends to move out of underdense regions and into overdense ones. This is sometimes described as void expansion, meaning that voids can grow as surrounding structures pull matter away. This flow pattern matters because it shapes where the remaining gas ends up, often leaving slightly higher density ridges at void edges and very low density interiors. Yet void interiors are not uniform. They can contain smaller filaments of dark matter and gas, sometimes called void substructure, on which small galaxies can form. The outer conditions therefore include a general trend of low density, but with internal variations. Another aspect of void conditions is the rate of interactions. In dense environments, galaxies collide, merge, and strip gas from each other. In voids, the average distance between galaxies is larger, so close encounters are rarer. This influences star formation histories. A galaxy in a void may retain its gas longer because it experiences fewer disruptive encounters and less stripping by hot intra-cluster gas. It may form stars more slowly but for a longer time, depending on its mass and its ability to accrete gas from the intergalactic medium. Yet this is not uniform. Some void galaxies can still undergo interactions with small neighbours, and some can have bursts of star formation triggered by internal processes. The point is that the environment reduces the frequency of strong external triggers. This can make void galaxies valuable for studying how galaxies evolve with fewer environmental pressures. The low-density environment also affects the presence of hot gas halos. Massive galaxies and groups can host hot gas that emits X-rays. In voids, massive groups and clusters are rare, so the volume-filling hot X-ray emitting gas is reduced. If an observation suggests widespread hot gas inside a void, that would be unusual under the consensus picture, unless the signal is actually from background clusters or from structures on the void edge. In the outer conditions, one expects the interior of a large void to be dominated by low-density dark matter and ionized gas with a sparse population of relatively small galaxies, and little in the way of massive hot luminous structures. However unusual does not mean impossible. Voids can contain isolated galaxies, small groups, and occasionally brighter systems depending on the details of the density field. A large void can also be the result of how a region is defined using bright galaxy tracers. If bright galaxies avoid a region but faint galaxies exist, there the region can appear emptier than it is in terms of total mass. Therefore, the outer conditions should be stated as expectations with room for measured variation. The word detected inside such a region becomes a question about consistency. Is the detection consistent with a low-density environment that still contains matter, or does it imply a concentration of matter or energy that would usually be associated with denser regions? At this stage, the calm approach is to treat the void as a low-density environment with thin, mostly ionized gas, a reduced local radiation field, fewer massive systems and fewer interactions, while acknowledging that faint substructure and small galaxies can still inhabit it. The next inward step is to move from these general conditions to the materials present, meaning the actual physical components, their states, and their measurable signatures without yet committing to a specific interpretation of any single report. In the broad outer environment of a void, the main materials present can be grouped into a few physical components, each with its own way of being inferred. The first is dark matter, which shapes gravity but does not emit light. The second is ordinary matter, mostly hydrogen and helium gas in intergalactic space, plus the gas dust and stars inside the few galaxies that inhabit the region. The third is radiation, which is not material in the sense of mass at rest, but which carries energy and interacts with matter. When a claim suggests an unexpected detection inside the Boötes Void, it often hinges on which of these components the signal traces. A calm evaluation begins by separating what is directly observed from what is inferred, because in a void, most important components are not directly visible. Dark matter is inferred from its gravitational effects. On the larger scales, the distribution of galaxies traces dark matter statistically because galaxies form in dark matter concentrations. In a void, the lower density of galaxies suggests a lower density of dark matter, but the relationship is not exact. Dark matter can form subtle structures in voids, including low-density filaments and small halos that may host faint galaxies. If a detection implies a mass concentration inside the void, one possible route is gravitational lensing. Weak lensing can measure average mass deficits, and in some cases localized mass features. Another route is galaxy motion, since gravity affects velocities, yet both routes require careful analysis and large data sets. Without these, claims about dark matter concentrations remain uncertain. In most reports, the detectable signals are tied more directly to ordinary matter, particularly gas and stars. The most abundant ordinary material by mass in intergalactic space is hydrogen, followed by helium. In the present day universe, much of this gas is ionized, meaning electrons are no longer bound to nuclei. Ionized hydrogen does not emit strong visible light unless it is relatively dense or heated in a way that drives emission. In the thin intergalactic medium, the gas is often detected through absorption rather than emission. Hydrogen absorption can be seen in ultraviolet spectra of bright background sources. Helium can also be traced, though it is more difficult. Heavier elements such as carbon, oxygen, silicon and iron can appear in absorption lines if the gas has been enriched by material expelled from galaxies. This enrichment can reach into low-density regions through winds and outflows over cosmic time. In a void, enrichment is expected to be lower on average because there are fewer galaxies to supply metals, meaning elements heavier than helium. Yet it is not necessarily absent. Even a small number of galaxies can seed the surrounding medium with metals, and material can also flow in from surrounding structures. Therefore, the chemical makeup of void gas can vary. A detection of metal absorption lines at the void distance would indicate that some enrichment has occurred along that line of sight. It would not by itself imply a dense structure, but it would constrain the history of gas exchange between void interiors and the surrounding web. Another material component is neutral hydrogen, where the electron remains bound to the nucleus. Neutral hydrogen is less common in the diffuse intergalactic medium because ultraviolet radiation tends to ionize it. However, neutral hydrogen can persist in denser pockets, particularly in galaxies and in their immediate surroundings. Neutral hydrogen can be detected through the radio emission line that arises from a change in the relative orientation of the electron and proton spins. This emission is weak but measurable for gas-rich galaxies. In voids, galaxies can be gas-rich and relatively isolated, which can make them good candidates for detection in neutral hydrogen surveys. A report of a detection inside the Boötes Void might therefore involve a previously unseen population of gas-rich dwarf galaxies. Such galaxies could be faint in optical light but conspicuous in radio. This would make the void seem less empty without contradicting the fact that it is underdense relative to the mean. A different kind of material is hot ionized gas at high temperatures. Hot gas emits X-rays through thermal processes when particles collide. This is common in galaxy clusters where gravity heats gas to very high temperatures. In voids, large reservoirs of such hot gas are not expected because deep potential wells are rare. Yet smaller halos and groups can still host warm or moderately hot gas, and shock heating can occur along filaments, even faint ones. The difficulty is that the resulting emission may be extremely faint. If an X-ray detection is reported toward a void, it must be tested against the possibility of background clusters, active galaxies behind the void, or instrument background. The presence of hot gas would suggest either a hidden mass concentration in an active galaxy, or a misplacement in distance unless other evidence supports a genuine void interior origin. Dust is another component, though it is typically associated with galaxies rather than with intergalactic space. Dust grains form in the outflows of evolved stars and in supernova explosions, and they are transported through galaxies and sometimes into their halos. In the intergalactic medium, dust density is low, but it may not be zero. Even small amounts of dust can redden background light. In voids, the expectation is that dust is even rarer because there are fewer galaxies. If a detection relies on optical colours, small dust effects can still matter for distance estimation. But dust itself is unlikely to generate a strong signal across a void volume. It is more likely to complicate measurements rather than to create an apparent object. Stars and stellar light are mostly confined to galaxies. Therefore, detections of starlight inside a void usually mean detections of galaxies. The galaxies may be small, low surface brightness, or isolated. They may have low star formation rates, making them faint in ultraviolet, or they may be gas-rich and forming stars slowly. In such cases, infrared observations can help trace older stars, while optical surveys can map the overall distribution. If a detection is described as not making sense, it might be because the object appears too bright, too massive, or too clustered for a void. Yet this again depends on distance, and on whether the object is truly inside the void interior or near its boundary, where filaments and groups are more likely. Another category of material is the energetic environments around black holes. An actively feeding black hole in a galaxy can produce strong radiation across many wavelengths, and can drive jets that emit radio waves. If such an active galaxy is found in a void, it is not impossible, because even a sparse galaxy population can include massive black holes. However, the probability is lower simply because there are fewer galaxies. Therefore, finding a rare object in a void can feel striking, but rarity alone does not violate physics. The correct approach is to quantify how rare it is given the void's galaxy count and volume, and to confirm the object's distance. Within the outer material inventory, the most stable statement is that a void contains a reduced amount of dark matter and ordinary matter relative to the mean, but it still contains both. The ordinary matter is mostly thin ionized gas, with some neutral gas in galaxies plus stars and dust inside those galaxies. The measurable signatures of these materials depend on wavelength and on method. A detection that seems to make no sense often becomes more grounded when it is connected to a specific material tracer and its expected abundance in an underdense environment. The next inward step is to focus on smaller scale components that can persist even when large galaxies are rare, including dust grains and other particles, and to examine how their signatures might be misread as something more dramatic if the observational context is not carefully controlled. Even within a region defined by a shortage of galaxies, there can still be a quiet population of small solids and particles. These include dust grains associated with galaxies, small particles carried in outflows, and the diffuse background of energetic particles that travel through intergalactic space. In the setting of the Boötes Void, the question is not whether particles exist at all, but how abundant they are, how they are distributed, and what signals they might produce or distort. A claim that something is detected inside the void can sometimes be traced back to how such particles scatter, absorb, or emit radiation, especially when the signals are near the limits of detection. A dust grain in astrophysical terms is a tiny solid particle often made of silicates, carbon-rich material, or mixtures that include heavier elements. Dust forms in the cool outer layers of evolved stars and in the debris of supernova explosions. It is then mixed into the interstellar medium of a galaxy, where it can absorb and scatter starlight. Dust is most abundant inside galaxies, where stars continuously produce it, and where gas density allows grains to survive and grow. In the low-density intergalactic medium, dust grains face a harsher environment. They can be sputtered, meaning eroded by collisions with fast ions in hot gas, and they are less likely to be replenished. Still, galaxies can expel dust into their halos through winds driven by star formation and supernova activity. Over long time, some of that material can reach intergalactic space. In a void, because galaxies are sparse, the overall dust density is expected to be low, yet it is not expected to be precisely zero, especially near the few galaxies that exist in the region, or near the boundary where outflows and filaments are more common. The observational importance of dust is often greater than its mass suggests because dust interacts strongly with your light. Dust preferentially absorbs and scatters shorter wavelength light. This can dim and redden the light from background sources. If the reddening is not properly accounted for, a background galaxy might appear to have colours that suggest a different redshift. In large surveys that rely on colours to estimate distances, even small dust effects can contribute to misclassification. In a void direction, where the number of galaxies is already low, misclassifying a small number of sources can change how sparse the region appears. This does not create a false void in a strong sense, but it can sharpen or soften the inferred boundaries. Dust can also create faint diffuse light through scattering, sometimes called diffuse galactic light, when it is produced by dust in the Milky Way scattering starlight. This is a foreground effect. In deep optical imaging, diffuse galactic light can appear as faint, wispy structures across the field. If not recognized, it can be mistaken for extragalactic low-surface brightness features. Because void studies sometimes push toward extremely faint surface brightness, limits fields may be chosen in regions of the sky that appear clean of bright stars and bright nebulae, yet diffuse galactic light can still be present. Therefore, a reported diffuse optical detection in the direction of a void must be tested against this foreground possibility. This is one reason multi-wavelength checks matter. Diffuse galactic light has a characteristic spectrum and correlation with dust maps. Another population of small solids is the dust and debris within galaxies, including the low-surface brightness outskirts. Some galaxies have extended halos of stars and faint tidal features that can be hard to see. If a void is mapped using bright galaxy catalogues, a very low surface brightness galaxy might be missed. Deep imaging can later reveal such galaxies. When such a galaxy is found, it can feel like something appeared in an empty place. Yet the emptiness was defined by survey limits, not by absolute absence. The same applies to small dwarf galaxies that have low star formation and therefore low brightness. These systems can remain hidden until sensitive imaging or radio surveys detect them. Dust can also emit. Grains absorb ultraviolet and optical light and re-radiate energy in the infrared. In voids, the lack of nearby bright galaxies reduces infrared background from local sources, but dust emission from the Milky Way remains a foreground. In far infrared maps, the sky can be dominated by cirrus emission from galactic dust. This emission is structured and can mimic faint extragalactic features. Therefore, an infrared detection associated with a void direction must be carefully cross-checked with galactic dust templates. Moving from dust to smaller particles, intergalactic space contains electrons and ions as part of the ionized gas. These particles can scatter photons through interactions such as Thomson's scattering, though in the thin intergalactic medium the effect is usually weak. However, in special cases, scattering by electrons in hot gas can imprint subtle signatures on background radiation. In galaxy clusters, for example, hot electrons scatter cosmic microwave background photons and produce a measurable distortion. In voids, the opposite effect might be considered, but because the gas density is low, any such imprint is small and difficult to detect. Claims in this category tend to be statistical and sensitive to systematics. Another particle population is cosmic rays' high-energy protons and nuclei that travel through space. Cosmic rays are produced by supernova remnants, active galaxies, and other energetic processes. Their density in intergalactic space is low, and measuring them directly beyond the solar system is extremely difficult. Their presence is inferred indirectly through gamma rays and radio emission produced when cosmic rays interact with gas and magnetic fields. In voids with low gas density and uncertain magnetic fields, the expected emission from cosmic rays is low. If diffuse radio emission is detected in a void direction, one possible explanation is synchrotron radiation from cosmic ray electrons moving through magnetic fields. For this to be widespread, there must be mechanisms to accelerate particles and maintain magnetic fields across large scales. Possible sources include jets from active galaxies, shocks along faint filaments, or relic magnetization from earlier cosmic times. The degree to which such processes fill void interiors remains uncertain. Observationally separating a true void interior signal from background and foreground sources is challenging. Confusion from unresolved radio sources, calibration artifacts, and emission from the Milky Way can all produce false diffuse patterns. Therefore, this class of detection is one where careful analysis is essential. The presence of particles also matters for how light is absorbed. Gas in the intergalactic medium can absorb ultraviolet light at specific wavelengths, producing a forest of absorption lines in spectra of background quasars. The density of these lines changes with environment. In voids, fewer absorption systems may be expected because gas density is lower, but the relationship is not simple, because even low-density gas can produce absorption if the path length is long. Therefore, finding absorption systems at the void distance is not itself contradictory. It becomes informative when the column density, meaning the number of atoms along the line of sight, and the presence of metals are measured. Those measurements can constrain how gas is distributed and enriched in underdense regions. At this stage, the calm conclusion is that small solids and particles provide both real content and real complications. They can create signals, especially in scattered light and diffuse emission, and they can distort measurements through extinction and background structure. A report that something is detected inside the Boötes Void can sometimes reduce to a problem of separating faint extragalactic signal from local foregrounds and instrumental residuals rather than a problem of new physics. Yet particles are also part of the real void environment, especially near the few galaxies within it, and near the boundary where matter flows and outflows accumulate. The next inward step is to move from these materials to energy sources, meaning the processes that can generate measurable radiation or acceleration within or near void interiors, while still keeping the discussion tied to known mechanisms rather than to dramatic framing. In a void environment, energy sources are fewer on average than in dense regions, but they are not absent. Energy sources here mean processes that inject heat light or fast particles into gas and dust, making those materials more visible or altering their state. The main cosmic energy sources remain the same everywhere: radiation from stars' radiation, and jets from actively feeding black holes, and the heating associated with gravitational collapse and shocks as matter flows. In a region like the Boötes Void, the difference is that the density of galaxies is lower, so the average rate of star formation and black hole activity per unit volume is reduced. Yet because the void volume is large, it can still contain rare energetic systems. It can also contain faint processes that become noticeable only because the usual bright background is reduced. To understand how an unexpected detection might arise, it helps to trace each energy source and its signature. The first and most common energy source is starlight. Stars form by gravitational collapse of gas within galaxies. Once formed, they emit light across a wide range of wavelengths. Massive young stars emit strongly in ultraviolet, while older cooler stars emit more in visible and infrared. In a void, galaxies tend to be smaller and may form stars more slowly, but some still form stars. The total starlight within the void volume is therefore lower, but individual galaxies can still be luminous, and some void galaxies can have ongoing star formation. The energy from starlight heats dust in galaxies producing infrared emission, and it ionizes nearby gas producing emission lines. If a survey detects ultraviolet or infrared emission in the void direction, it may simply be tracing star formation in void galaxies that were previously uncatalogued. A second energy source is supernova explosions. When massive stars reach the end of their lives, they explode and release large amounts of energy. Supernova heat surrounding gas drive shocks and accelerate particles. In a void galaxy with ongoing star formation, supernova can create winds that push gas and dust out of the galaxy. Over time, these winds can carry metals into the surrounding intergalactic medium. Even if void galaxies are sparse, a few active ones can influence their local environment. The effects are typically confined to regions near the galaxies, but because the intergalactic medium is thin, outflows can expand more easily than in dense environments. This can produce extended halos of enriched gas that are detectable in absorption against background sources. Therefore, a detection of metal absorption lines inside a void can be consistent with normal stellar feedback operating in isolated galaxies. A third energy source is active galactic nuclei, meaning the bright emission produced when gas falls into a supermassive black hole at the center of a galaxy. The process converts gravitational energy into radiation, and sometimes into jets of fast particles. Active galactic nuclei can emit strongly in X-rays, ultraviolet, optical infrared, and radio. They can also ionize gas far from the host galaxy. In a void, finding an active galaxy is less likely per unit volume, because galaxies are fewer, but it is not forbidden. A single active galaxy can dominate the energy output in its neighborhood, and can produce radio jets that extend far beyond the visible galaxy. Such jets can inflate lobes of relativistic plasma that emit synchrotron radiation in radio bands. If a radio detection inside the void is linked to an active galaxy, the apparent contradiction may weaken. The question then becomes whether the host galaxy truly lies inside the void interior, and whether the radio structure is as large and as diffuse as claimed. Radio jets and lobes can appear diffuse, and if they are very extended, they can be confused with other diffuse emission. Yet their association with a compact core and their spectral properties can help identify them. Another energy source is gravitational heating. Matter in the universe flows under gravity. In dense regions, gas falls into deep potential wells, shocking and heating to very high temperatures. In voids, the gravitational potentials are shallower, but matter still flows. Gas can still experience mild shocks along the faint filaments and sheets that thread void interiors. These shocks can heat gas to warm temperatures and can accelerate particles. The expected signals are weak, but over large path lengths they can accumulate. Some theories suggest that a significant fraction of ordinary matter in the present universe resides in warm, hot intergalactic medium, meaning gas at temperatures of hundreds of thousands to tens of millions of degrees, often in filaments around and between clusters. In void interiors, the fraction of such warm, hot gas is expected to be lower, but not necessarily zero. Detecting warm-hot gas is challenging, and claims often involve subtle absorption lines in ultraviolet or X-ray spectra or faint diffuse emission. Therefore, a detection framed as surprising might arise from an attempt to detect this gas in an underdense region. The interpretation depends on whether the signal is truly from void gas, or from structures near the void boundary, or from unrelated foreground or background sources. Energy can also enter a void from outside. Radiation travels and energetic particles can propagate. The ultraviolet background that ionizes intergalactic gas is produced by galaxies and quasars across the universe. A void does not block this radiation. Therefore, even if local sources are scarce, the void, gas remains exposed to a global radiation field. This field keeps much of the gas ionized and influences its chemistry. The field can vary with position because of the distribution of sources and because of absorption along paths, but it is not confined to dense regions. Similarly, gamma rays and other high-energy photons can travel long distances. Their interactions with intergalactic fields and backgrounds can produce secondary particles. Some studies use gamma-ray observations of distant blazars to infer properties of intergalactic magnetic fields in voids, because the paths of secondary particles are affected by magnetic fields. The uncertainties remain significant, but the key point is that voids are part of the broader cosmic environment, not isolated chambers. Another source of energy is the cosmic microwave background itself, not as a source of heating in the usual sense, but as a field that can be slightly altered by structures along the line of sight. As photons pass through evolving gravitational potentials, they can gain or lose a small amount of energy. This effect is tiny and difficult to measure, but large voids can in principle leave subtle imprints. Claims in this category depend on statistical detection and careful control of noise and selection. If a report points to a feature in the cosmic microwave background associated with the Boötes Void, the surprise may come from the strength or scale of the feature. The evaluation then turns on how robust the correlation is, and whether the effect is consistent with known physics and typical void properties. In all these cases, the common thread is that energy sources in a void are reduced in number, but can still be present, and rare systems can stand out against a quieter background. A detection that sounds like it makes no sense can be the result of rarity combined with survey expectations. A large volume with few galaxies can still contain one unusual, active galaxy, one small group or one extended radio structure. It can also contain faint signals that become visible only when observers push to very low brightness levels and remove bright foregrounds. The next inward step is to consider boundaries and transitions, because many surprising detections arise not in the deepest interior, but near the edges where matter accumulates, and where definitions of the void's interior are most sensitive to survey choices. Boundaries in a cosmic void are not walls, but transitions in density. Yet these transitions matter because many apparent surprises depend on whether something lies in the deepest interior or nearer to the edge where the cosmic web thickens. The Boötes Void is defined by a large region of low galaxy density. Around it, the cosmic web forms filaments and sheets where galaxies are more common. The boundary can therefore be thought of as a gradient from underdense to more typical or overdense regions. In practice, the boundary is drawn by a chosen definition. One definition might be the region where galaxy density falls below a fixed fraction of the average. Another might be the connected underdense region identified by an algorithm. A third might be the set of largest empty spheres found in the galaxy distribution. Each definition yields a somewhat different outline. When a detection is assigned to the void, the distinction between interior and edge becomes important, because the physical conditions change across that gradient, and because the probability of encountering galaxies and groups rises toward the edge. The outermost view of a boundary begins with geometry. A void is a three-dimensional shape. Its projection on the sky is not enough to define where it begins and ends. Distance matters, and distance errors blur the boundary. Even with accurate redshifts, the boundary can be fuzzy because density itself is measured with limited sampling. If a survey includes only bright galaxies, the boundary will be drawn by those galaxies. Faint galaxies that lie within the boundary might remain unseen, and the region might appear emptier. When deeper surveys find those faint galaxies, the density gradient becomes more detailed, yet the boundary remains a transition rather than a sharp edge. This has a practical consequence. An object near the boundary might be reported as inside the void if the void is defined broadly, or as outside if defined narrowly. Therefore, the first calm step in evaluating a claim is to check whether the reported location is well within the interior under multiple definitions, or whether it sits near an uncertain boundary. The physical transition at the boundary also includes matter flows. In the cosmic web, matter tends to move from underdense regions toward overdense ones. This flow is slow operating over billions of years, but it shapes the distribution. Void interiors can be thought of as regions where matter has been evacuated relative to the mean. The edges can be thought of as regions where matter piles up. This is not a pile in the everyday sense, but a relative enhancement in density. Gas and dark matter can form sheets and filaments around the void. Galaxies are more common there, and small groups can form. If a detection seems too rich or too energetic for a void, it may in fact be part of this boundary structure. The boundaries can also contain thin filaments that extend into the void. These filaments may be sparse in bright galaxies, but can still host faint galaxies and gas. Because the filaments are narrow, they can be missed in coarse maps, yet they can provide channels for gas accretion into the few galaxies that live in the void, and can host shocks that heat gas. Therefore, a detection of gas diffuse emission or an unexpected galaxy population might trace such internal filaments rather than a uniform void interior. Another boundary issue is the effect of redshift space distortions. Galaxy redshifts include contributions from cosmic expansion and from galaxy motions. A galaxy moving toward or away from the observer has its redshift slightly altered by its peculiar velocity. In dense clusters, this effect can smear galaxy positions along the line of sight. In voids, the effect is smaller but not absent. Galaxies tend to flow outward from void interiors toward denser surroundings. This coherent motion can distort the apparent shape of a void in redshift space. A void may appear slightly elongated or compressed along the line of sight depending on how velocities project. This can affect boundary placement and can shift objects across the boundary in a redshift space map. Careful analyses attempt to correct for this, but the corrections depend on models and on the sampling of galaxies. Therefore, boundary assignment remains a source of uncertainty. The question of transitions is also relevant to observational selection. Surveys may have varying completeness with direction and distance. Near the edge of the survey, footprint density estimates can be biased because there are fewer galaxies counted due to geometry. If the Boötes Void lies near such a region for a given survey, boundary definitions can be affected. Modern surveys handle these effects with masks and corrections, but residual issues can remain. A detection that seems to sit inside the void could be influenced by these mapping uncertainties. The transition also matters for interpreting signals like diffuse radio emission or X-ray emission. If such emission is detected toward the void, one must ask whether it could come from a filament on the boundary that lies along the line of sight. A filament is a three-dimensional structure. If the line of sight passes through a filament at the void's distance, the filament could be associated with the void region, depending on the mapping definition, but physically it may represent a denser structure within or at the edge of the void. In that case, the detection would not reflect the deepest low-density interior, but rather the structured transition zone. This is not a semantic trick. It reflects the real complexity of the cosmic web where voids and filaments interpenetrate, and where boundaries are not smooth. Another transition is temporal. The Boötes Void is observed at a certain redshift range, meaning at a certain look-back time. The cosmic web evolves. Voids grow and merge over time. The density contrast between voids and filaments increases as structure formation proceeds. Therefore, the physical state of a void depends on when it is observed. A void at higher redshift is less evolved, and may contain more material relative to the mean than a void of similar size at lower redshift, though the details depend on cosmology and on how the void is defined. If a detection is claimed at the void distance, the cosmic time matters for expectations. Yet within the bounded interval of the Boötes Void, as commonly discussed, the look-back time is not so extreme that structure formation is radically different from the present day. The void is part of the nearby cosmic web in the broad sense. Still, small differences in redshift within the void volume correspond to differences in look-back time that can matter for interpreting star formation and galaxy evolution in the few void galaxies. In calm terms, boundaries and transitions are the places where apparent contradictions often arise. A void is defined statistically, and its edges are where small changes in definition can move an object from inside to outside. Physical conditions also change most rapidly there, making the edges more capable of hosting denser gas groups of galaxies and shocks that produce detectable emission. Therefore, before moving inward to more detailed mechanisms, the boundary region must be understood as a gradient with internal substructure. A detection that seems to make no sense in a deep void interior may make more sense if it lies in a boundary filament or in a substructure that threads the void. To decide, one needs secure distance measurements, consistent void definitions, and an understanding of how the line of sight intersects three-dimensional structures. The next inward step is to move into the mid-region environment, treating the void not only as a map and a boundary, but as a volume with internal variations in gas density, temperature, and small-scale structure that can support certain physical processes even when galaxies are rare. Entering the next inward region means leaving the broad definition of the Boötes Void as a mapped underdensity and focusing on what the void interior can be like as an environment in its own right. Even within the interior, the density is not uniform. There are gradients, pockets, and thin threads of matter. The mid-region environment can be described through the behavior of gas and dark matter on scales smaller than the full void, but larger than individual galaxies. At this scale, the dominant features include low-density dark matter structure, diffuse ionized gas that follows gravity, and the sparse set of halos where small galaxies can form. The key point is that the interior is quiet rather than empty. Quiet means fewer strong shocks, fewer intense radiation sources, and fewer frequent interactions, but it still means ongoing physical processes shaped by gravity expansion and radiation backgrounds. In the mid-region, dark matter forms a smooth but not featureless distribution. Simulations show that void interiors can contain smaller dark matter halos and faint filaments. These structures are lower in mass and contrast than the filaments around the void, but they can still exist. Ordinary gas tends to follow these structures because gravity pulls gas into potential wells. Yet the gas response is moderated by pressure and by its thermal history. In low-density regions, gas can remain diffuse, and it can take a long time to cool and condense. The ionized intergalactic medium in the void interior is therefore expected to be thin and warm, with temperatures often set by a balance between photoheating from ultraviolet background radiation and cooling from expansion and radiation. In plain terms, the gas is warmed by light that strips electrons from atoms and cools as it spreads out and as it radiates weakly. The details depend on density, on the strength of the ultraviolet background, and on the presence of nearby galaxies that can add local radiation. One mid-region feature is the presence of small galaxies that are hard to detect. In a void, the galaxies that do form may be dominated by gas and have low surface brightness, meaning their light is spread out and faint per unit area. Traditional surveys that focus on bright galaxies can miss them, especially if they are small and their light is close to the sky background. Deeper imaging and radio surveys can reveal them. In the mid-region, these galaxies are important because they represent concentrated pockets of gas and stars within the diffuse medium. Their star formation can be slow and intermittent. Their feedback, meaning the impact of supernovae and stellar winds, can push gas outward into the surrounding medium. Because the surrounding pressure is low, outflows can expand farther. This can create extended halos of gas around void galaxies, making them more detectable in absorption. It can also distribute metals into the nearby intergalactic medium. Therefore, the mid-region environment may include small enriched pockets around the few galaxies, even while the broader volume remains metal-poor. A detection described as surprising might at this scale be a sign of such a pocket, rather than a sign of a large dense structure. Another mid-region feature is the relationship between gas density and detectability. In emission, many signals depend on density squared because they require particle collisions. In a low-density region, emission is therefore strongly suppressed. In absorption, the dependence is closer to linear with column density, meaning the total number of particles along the line of sight. A long path through low-density gas can still produce measurable absorption. This is one reason void interiors can be studied with absorption even when emission is nearly invisible. It is also a reason why a detection can be misread. An absorption line can be strong evidence for gas, but it does not necessarily imply high local density. It may imply a long path length through modest density. In a void, the path length can be large. Therefore, a detection of gas through absorption inside the void can be consistent with thin gas spread over large scales. The mid-region also includes the possibility of temperature variations. Gas in void interiors is less shocked than gas in filaments, but it can still be heated by several mechanisms. One is photoheating, which is widespread. Another is mild gravitational heating as gas flows along faint structures. A third is feedback from galaxies which can heat local volumes. Because the density is low heated, gas can retain its heat longer since cooling is less efficient. Cooling in such gas occurs through radiation from ions and through adiabatic expansion, meaning cooling as the gas expands. The balance can produce a range of temperatures, but generally below the hottest cluster gas. These temperature variations matter because different ions exist at different temperatures, and therefore absorption line species can indicate the thermal state. If a detection report mentions certain ions at the void distance, it may be tracing warm gas rather than cold gas. The mid-region environment also has a velocity structure. Matter flows out of void interiors toward denser regions. This flow can create coherent velocity gradients. Gas and galaxies can have peculiar velocities relative to the pure expansion. These velocities can broaden absorption lines and can affect how redshifts are interpreted. In a void, velocities are generally lower than in clusters, but coherent flows can still be significant over large scales. Therefore, when an absorption system is found in a void, its velocity relative to nearby galaxies can provide clues about whether it is associated with a galaxy halo, a faint filament, or more diffuse gas. Yet such interpretations require careful mapping of nearby galaxies, including faint ones. Another mid-region aspect is the ionization state of gas. Ionization depends on the ultraviolet background and on density. In low-density gas recombination, the process where electrons reattach to nuclei is slow. Therefore, once gas is ionized, it can remain ionized. This means that neutral hydrogen fraction in void gas is low, making neutral hydrogen emission difficult to detect, except in denser structures like galaxies. However, even a small neutral fraction can produce absorption lines because absorption depends on column density. Therefore, the presence of hydrogen absorption does not necessarily mean the gas is neutral overall. It can mean the gas is mostly ionized with a small neutral component. This is a subtle but important point in interpreting detections. In the mid-region, the environment is also influenced by the fact that voids are part of a network. Thin filaments can connect the void interior to the surrounding web. Gas can slowly accrete along these pathways. Over long times, this accretion can feed star formation in void galaxies. The accretion may be colder and smoother than in dense environments because there are fewer strong shocks. Yet the difference is one of degree. The process remains the same. Gravity draws gas into halos, gas cools, and stars form when gas becomes dense enough. A detection that suggests unexpected activity inside a void might be evidence that such pathways are present and more effective than assumed in a simplified picture. The mid-region focus therefore reframes the void interior as a low-density, low-pressure environment with faint structure, slow flows, and sparse small galaxies embedded in thin ionized gas. It is a setting where absorption is often more informative than emission, and where rare energetic events can stand out. The next inward step is to examine chemistry within this environment, meaning how elements and ions behave under these densities and radiation fields, and how chemical signatures can clarify whether a detection is local to a void galaxy, spread through diffuse gas, or instead linked to a structure at the boundary. Chemistry in the interior of a cosmic void is shaped by simplicity and scarcity. The dominant elements are hydrogen and helium created in the early universe. Heavier elements, often called metals in astronomy, are made later inside stars and spread outward by winds and explosions. In a region like the Boötes Void, where galaxies are sparse, the average enrichment by heavy elements is expected to be lower than in dense regions. Yet enrichment is not uniform, and even a small number of galaxies can seed their surroundings. The chemistry that matters for detection is therefore a combination of primordial composition, ionization states controlled by background radiation, and localized metal enrichment around the few galaxies and along faint structures. The measurable chemical signatures appear mainly as absorption lines, and more rarely as emission lines. A calm assessment begins by separating elemental abundance from ionization. A gas can contain a certain amount of an element, but whether that element is detected depends on which ionization state it occupies. Ionization state means how many electrons have been removed from an atom. The ionization state depends on temperature, radiation field, and density. In the diffuse intergalactic medium, ultraviolet photons from the cosmic background ionize hydrogen and many metals. Therefore, the gas can be mostly ionized even when it is not hot in the everyday sense. In this regime, hydrogen can be mostly ionized while still leaving a detectable fraction of neutral hydrogen that produces absorption at ultraviolet wavelengths. This is why hydrogen absorption can trace very thin gas. The strength of the absorption depends on column density, meaning the total number of neutral hydrogen atoms along the line of sight, and on the broadening, which depends on temperature and motion. In void interiors, the neutral fraction can be low, but the path length can be large, making absorption possible. For metals, similar logic applies. Carbon, oxygen, silicon, and other elements can exist in multiple ionization states. Some states are most common in photoionized gas, where radiation sets ionization, while others are most common in collisionally ionized gas, where high-temperature collisions remove electrons. Therefore, detecting a particular ion can reveal something about the gas conditions. For example, certain oxygen ions are more common at higher temperatures, yet interpretation requires care because the same ion can appear under different conditions depending on the radiation field. In a void, the ultraviolet background may be somewhat weaker locally, but it is not absent. Therefore, photoionized gas remains common. If a detection inside the void involves metal absorption, it might indicate pockets of enriched gas around galaxies or along filaments. The metals themselves must have come from stars. This implies at least some history of star formation and outflow. It does not require a dense cluster. A small dwarf galaxy can enrich its surroundings over time. In low pressure, environment's outflows can travel farther, potentially enriching larger volumes at low levels. Therefore, a surprising chemical signature could in principle reflect effective transport rather than unexpected mass concentration. Another chemical process relevant in void interiors is cooling. Gas cools by emitting radiation through transitions in ions. The efficiency of cooling depends on metallicity, meaning the abundance of heavy elements. Metal-poor gas cools less efficiently at certain temperatures because it lacks the ions that radiate strongly. In void interiors, if metallicity is low, gas may remain warmer and more diffuse, slowing the formation of dense clouds that could become stars. This can contribute to the lower galaxy formation efficiency in voids. However, near existing galaxies, metallicity can be higher due to enrichment allowing more efficient cooling and potentially supporting ongoing star formation. Therefore, the chemical landscape is patchy, mostly primordial-like diffuse gas with localized enriched regions. A detection of emission lines such as those from ionized hydrogen in star-forming regions would likely be tied to a galaxy, rather than to diffuse intergalactic gas because emission requires higher density. An important chemical clue in absorption studies is the ratio of different ions. By measuring multiple lines, astronomers can model the ionization conditions and infer density, temperature, and metallicity. In a void, these inferences can test whether an absorber is consistent with diffuse intergalactic gas, or whether it is more like a galaxy halo. A galaxy halo absorber might show higher metallicity and certain ion ratios. A diffuse void absorber might show lower metallicity and different ratios. Yet uncertainties remain because the radiation field is not perfectly known and because the geometry of the gas is unknown. A single line of sight samples only one path. Therefore, chemistry can constrain possibilities, but rarely provides a unique answer without additional context, such as the presence of nearby galaxies and their distances. Another chemical aspect involves molecules and dust-related chemistry. In the diffuse intergalactic medium, molecules like molecular hydrogen are rare because the density is too low, and ultraviolet radiation tends to break molecules apart. Molecules form more readily in dense shielded regions, often on the surfaces of dust grains. In void interiors, dense molecular clouds are expected mainly inside galaxies. Therefore, detecting molecules or strong dust signatures at the void distance would likely point to a galaxy or a dense cloud associated with a galaxy rather than to diffuse void gas. If a report suggests unexpected molecular absorption inside a void, the calm approach would be to look for an associated faint galaxy or for a misidentified distance. Conversely, the absence of molecules is not surprising and would be consistent with thin ionized gas. Chemical signatures can also be influenced by the history of reionization and by subsequent heating. The ultraviolet background evolves over cosmic time. For the nearby universe, the background is shaped by galaxies and quasars. Variations in this background can alter ionization fractions. In a void, fewer local sources might reduce the background slightly, potentially increasing the neutral fraction of hydrogen in some regions. This could make absorption somewhat stronger for a given gas density. This is a subtle effect and depends on details, but it illustrates how void chemistry is not simply scaled down. The environment changes the balance. Another subtlety is that metals can travel. Galactic winds can carry enriched gas into the intergalactic medium. In low-density environments, the winds can expand and mix. Over long times, a void interior can accumulate low levels of metals even if star formation is sparse. Therefore, finding metals in void absorbers is not inherently contradictory. The level of metallicity and the spatial distribution are the key. High metallicity would suggest proximity to a galaxy, or strong enrichment, while very low metallicity would suggest more pristine gas. Reports that say something makes no sense sometimes overlook this gradient and present any metal detection as surprising. In reality, the surprise would depend on the measured metallicity and on how it compares with models of enrichment and transport. Within the inward progression, chemistry provides a bridge from environment to process. It links the presence of galaxies to the state of surrounding gas. It also provides a way to test whether a detection is more likely to be local, such as a galaxy halo, or more diffuse, such as intergalactic gas spread through the void. The next inward step is to examine formation and breakdown processes, meaning how structures in such an environment can form, persist, or dissolve. This includes how gas accretes into halos, how star formation proceeds in isolated systems, how feedback reshapes local gas, and how faint filaments can maintain themselves within the broader underdense region. Formation and breakdown processes within a void interior are governed by the same physical laws as elsewhere, but they unfold under different constraints. The constraints are low density, low pressure, and long timescales. In dense regions, gravity gathers matter quickly into large halos, shocks heat gas strongly, and interactions between galaxies reshape structures. In a void, gravity still gathers matter, but the initial conditions are underdense, and the surrounding pull draws matter outward. As a result, structures that form tend to be smaller, more isolated, and more fragile. A detection that appears unexpected inside the Boötes Void can often be understood by tracing which process could create the observed signal in such a quiet environment and which processes could erase it. The first formation process is the growth of dark matter halos. Dark matter halos form from small density fluctuations in the early universe. Even in an underdense region, some fluctuations can be above the local average, allowing halos to form. However, the distribution of halo masses shifts. There are fewer massive halos and relatively more low-mass halos. This matters because the ability of a halo to gather gas and form stars depends strongly on its mass. Low-mass halos have shallow gravity, making it easier for gas to be heated and pushed out. They can also be affected by the ultraviolet background, which can keep gas warm enough that it does not collapse easily. Therefore, many low-mass halos in voids may contain little or no star formation, and remain dark in optical surveys. This produces a natural mechanism for an apparently empty region that still contains structure and dark matter. A detection that implies mass or gas inside a void may therefore be tracing these low-mass halos or the faint galaxies that form in the higher end of this low-mass range. The second formation process is gas accretion. Gas follows gravity and tends to fall into halos. In dense regions, accretion can be violent with shocks at the halo boundary, heating gas to high temperatures. In voids, accretion can be smoother, partly because inflows are weaker, and partly because the gas density is lower. Gas may accrete along thin filaments that thread the void. These filaments can be faint and hard to detect, but they can supply gas to small galaxies. If a detection involves neutral hydrogen, or ongoing star formation in a void galaxy, sustained gas accretion is a plausible supporting process. The presence of accretion also implies that void interiors are not static. Gas continues to move and rearrange, even if slowly. Breakdown processes begin at the same time. Gas in low-mass halos can be prevented from cooling by the ultraviolet background. Photoionization heats gas and reduces its ability to collapse. This can suppress star formation in the smallest halos. In addition, when stars do form, feedback can be disproportionately strong relative to the shallow gravity. Supernova explosions and stellar winds can drive gas out of dwarf galaxies. In a low-pressure environment, the outflow can expand and escape more easily. This can reduce future star formation by removing fuel. It can also enrich the surrounding medium with metals. Therefore, void galaxies can undergo slow gas accretion periods of star formation then outflows that suppress further activity followed by gradual replenishment. A detection of enriched gas in absorption inside a void could be a remnant of such outflows. A detection of a gas-rich low-luminosity galaxy could be a system that has retained gas but forms stars inefficiently. Another formation process is the creation of extended low-surface brightness structures. Because interactions are rarer in voids, tidal features from galaxy encounters are less common on average. Yet when interactions do happen, they can produce faint stellar streams and extended disks. These features can persist for long times because there are fewer subsequent encounters to disrupt them. Deep imaging might reveal large diffuse galaxies within voids that were missed in brighter surveys. Such galaxies can appear surprising because they contradict the simple expectation that void galaxies are always small. In reality, void environments can allow disks to remain undisturbed, potentially growing large in size while remaining low in star formation intensity. A very extended faint galaxy might therefore be a natural outcome of long quiet evolution rather than an anomaly. The breakdown process for such a galaxy would be internal, such as gradual gas depletion rather than external stripping. Another set of processes concerns active galactic nuclei. If a void galaxy hosts a supermassive black hole that becomes active, the resulting radiation and jets can be significant. The formation of a powerful active nucleus requires the black hole to be fed. Feeding can occur through internal instabilities in the galaxy disk, through minor mergers, or through gas inflow triggered by interactions. Even if interactions are rarer, they are not impossible. A rare event in a large volume can still occur. If an active galaxy appears in a void, it may stand out strongly. The jets can inflate radio lobes that persist for millions of years. These lobes can be detectable as diffuse radio emission. In a low-density environment, the lobes can expand farther, potentially producing large structures. Their breakdown occurs through radiative losses and through mixing with surrounding plasma. Therefore, a detection of diffuse radio structure inside a void might trace the relic of an active galaxy episode. The interpretation would require identifying a host galaxy at the same distance and checking whether the radiomorphology is consistent with jet-powered lobes. Another process involves shocks and particle acceleration. Even in voids, gas can experience shocks along faint filaments or at the boundaries of expanding structures. Shocks can accelerate electrons to high energies, producing synchrotron emission if magnetic fields are present. The existence and strength of intergalactic magnetic fields in voids remains uncertain, but it is plausible that some magnetic field exists seeded by early universe processes or by outflows from galaxies. If so, shocks could produce weak diffuse radio emission. Detecting such emission is difficult and subject to confusion with foregrounds and background sources. Yet if robust, it would provide information about the energy budget and magnetization of void interiors. The breakdown of such emission would be rapid in radiative terms because high-energy electrons lose energy. Therefore, sustained emission would require either ongoing acceleration or repeated events. This sets constraints on any claim of widespread radio glow in a void. Formation and breakdown also apply to gas clouds and absorbers. An absorption system seen in a quasar spectrum might represent a filament, a galaxy halo, or a more diffuse region of slightly higher density gas. Such structures can form as gas collects in dark matter potentials or as outflows create shells and clouds. They can break down through mixing and expansion. In low-density environments, mixing can be slower, allowing structures to persist. Yet the same low density can make them hard to detect except along fortunate lines of sight. Therefore, the presence of an absorber does not necessarily imply a common condition. It may reflect a sampling of rare, persistent structures. In calm terms, the processes within a void interior allow for faint galaxies, enriched gas pockets, extended low surface brightness systems, rare active nuclei and weak shocks, all within the bounds of known physics. What makes a detection feel like it makes no sense is often the mismatch between a simplified picture of emptiness and the real range of structures that can form in underdense regions. The next inward step is to approach the inner zone where the discussion narrows to how observers test and retest the origin of a surprising signal separating genuine void, interior phenomena from overlap along the line of sight and from the limits of instruments and surveys that shape what can be seen. Approaching the inner zone of the claim means focusing on how a surprising signal is checked against the most common pathways to misplacement and misinterpretation. At this stage, the setting is no longer the full void and its broad environment, but the narrower problem of whether the detected phenomenon truly belongs to the void interior. The inward movement is a movement in certainty. The question becomes which measurements lock down distance, which measurements isolate the signal from foreground and background, and which measurements test whether a proposed physical mechanism is consistent with the data. In calm practice, this is where many claims either strengthen through cross-checking or soften when alternative explanations remain plausible. One core test is distance confirmation. If the detection is a galaxy or a compact source, the strongest anchor is a spectroscopic redshift. A spectrum reveals features whose rest wavelengths are known, and the shift gives a robust distance estimate under standard cosmology. A photometric redshift can be useful, but it is less secure. Therefore, moving inward means asking whether a spectrum exists, whether it is of sufficient quality, and whether its redshift places the source within the void's defined redshift range with margin. Margin matters because void boundaries are fuzzy, and because redshift errors, though often small, exist. If the detection is diffuse, emission distance is harder. In that case, an inward test is to search for associated spectral lines in the emission that provide a redshift, or to identify a host structure such as a galaxy that can be placed in distance and plausibly powers the emission. Without such anchoring, a diffuse signal can remain ambiguous. Another test is association with known structures. If a claimed object lies in the void direction, it is important to map the surrounding area for galaxies at similar redshifts. A genuine void interior object should not sit within an unseen cluster of galaxies at the same distance. If deeper surveys reveal a group, the object might belong to a small filament or boundary structure. Conversely, if the area remains sparse, even in deep data, the void interior association strengthens. This mapping must include faint galaxies where possible, because void populations can be dominated by low luminosity systems. A further test is whether the void definition used for the claim matches modern surveys. A void identified in earlier data may have boundaries that change with newer data. Therefore, an inward check is to compare the object location against multiple void catalogues and definitions. If it lies within the interior across methods, the placement becomes more robust. If it lies inside only under one definition, especially one based on shallow data, the claim becomes less secure. Another inner zone check is the line of sight inventory. The direction toward the Boötes Void still passes through many distances, so one must account for foreground and background sources. In optical and infrared, star contamination and galactic dust patterns must be considered. In radiogalactic synchrotron emission and unresolved background radio sources can produce confusion. In X-rays, particle background and diffuse galactic emission can mimic faint extended sources. Therefore, the inward approach includes tests that a signal persists across independent datasets and instruments. For example, a diffuse radio feature that appears in one survey should be checked in another survey at a different frequency, and with different calibration if possible. A diffuse optical feature should be checked against dust maps, and should be tested for correlation with known galactic cirrus structures. A claimed X-ray glow should be checked for point source contamination and compared with background models. Consistency across methods does not guarantee truth, but inconsistency often indicates artifact. Another test is morphological and spectral plausibility. If the detection is radio emission, its spatial shape and spectral index, meaning how brightness changes with frequency, can help distinguish between synchrotron emission from jets and lobes, thermal emission from ionized gas and foreground contamination. Synchrotron emission typically shows a characteristic frequency dependence and can have polarization. If polarization is detected, it can support a synchrotron interpretation. If the emission aligns with a galaxy position and shows lobe-like structure, a jet origin becomes plausible. If it is smooth and follows galactic dust structure, a foreground becomes more plausible. Similarly, in optical imaging, a low-surface brightness galaxy should show a coherent shape and a color consistent with a stellar population, while diffuse cirrus often shows filamentary patterns correlated with dust maps. In absorption, studies line widths and ion ratios can distinguish between photoionized gas and collisionally ionized gas. These distinctions are not absolute, but they constrain models. In the inner zone, the goal is to narrow the model space without exaggeration. Another important inward test is statistical expectation. A large void still contains a finite number of galaxies. If one searches a huge volume, rare objects can appear simply because the volume is large. Therefore, a claim that something makes no sense should be tested against expected number counts. For example, if the detection is an active galaxy, one can estimate how many active galaxies might exist in a volume of that size, given the average space density of such objects. Even if the density is lower in voids, the expected count may not be zero. Therefore, the surprise may be emotional rather than statistical. Similarly, if the detection is a faint galaxy population, deeper surveys might be expected to find some. The inner approach uses probability to temper language. Another test is environmental consistency. If a detection implies high gas density, high temperature, or strong radiation fields across a large region, that must be reconciled with the void environment. For instance, a claim of a hot cluster-like X-ray halo would require a massive gravitational well. In a void interior, that would be rare. Therefore, the first check is whether the inferred mass is supported by lensing or by galaxy velocity dispersion. If not, a background cluster becomes a plausible explanation. If mass evidence exists, then the claim becomes that the void contains a massive structure, which would be an unusual but not impossible configuration depending on how the void is defined and on the scale of the structure. Another example is a claim of widespread diffuse radio glow. That would require either widespread particle acceleration and magnetic fields, or a superposition of many unresolved sources. An inner zone check is to subtract known point sources and test whether the residual remains. Another is to look for correlation with known large-scale structures. The inward approach therefore involves careful subtraction, cross-correlation, and repeat observation. At this stage, the topic is not about mysteriousness, but about method. A signal inside a void can be real and still be hard to interpret. It can also be an alignment effect. The inner region is where the evidence is weighed secure distance, multi-wavelength consistency, morphological plausibility, and statistical expectation. If these checks are satisfied, the claim becomes a grounded statement about an object or process in an underdense environment. If they are not, uncertainty remains. The next inward step is to focus on the smallest mechanisms relevant to what is actually detected, whether that is the microphysics of radiation and particle acceleration, the gas ionization balance, or the internal structure of a faint galaxy, and to describe what is known and what remains uncertain without forcing a single dramatic conclusion. Microscale mechanisms become relevant when the detection has been narrowed to a likely physical category. At this inward level, the focus is not the whole void or the broad survey map, but the local processes that produce the signal. The microscale is still physical and measurable. It includes how gas absorbs and emits light, how particles gain and lose energy, how magnetic fields influence motion, and how stars and black holes shape their surroundings within a single galaxy or a small region of intergalactic space. In the context of the Boötes Void, the microscale does not imply exotic physics. It implies the ordinary mechanisms operating in a low-density setting, sometimes with different balances than in denser environments. If the detection is an absorption feature attributed to void gas, the microscale mechanism is the interaction of photons with atoms and ions. An absorption line forms when photons of a specific energy are absorbed by an atom or ion, lifting an electron to a higher energy state. The probability of absorption depends on the number of absorbing particles along the line of sight, the distribution of their velocities, and the radiation field. In thin gas particles have thermal motion, and they can also have bulk motion. Thermal motion broadens the line. Higher temperature yields larger particle speeds and broader lines. Bulk motions can shift and spread lines. The line shape can therefore provide clues about temperature and turbulence. Another key microscale mechanism is ionization balance. In photoionized gas, ultraviolet photons strip electrons, while recombination returns electrons to nuclei. The balance depends on density because recombination requires encounters between electrons and ions. In low density, void gas recombination is slow, so ionization can remain high, even when the radiation field is weak. This means that the same column density can correspond to very different physical densities depending on ionization. Therefore, microscale modeling is required to infer density and metallicity from observed lines. The modeling includes assumptions about the ultraviolet background spectrum. Uncertainty in that background translates into uncertainty in inferred properties. This is not speculation. It is direct consequence of the physics of ionization. If the detection involves emission from gas microscale mechanisms, include collisional excitation and recombination emission. Emission lines appear when electrons collide with ions and excite them, and then the ions radiate as they return to lower energy states. The rate depends strongly on density and temperature. In void interiors, diffuse gas densities are low, making emission weak. Therefore, measurable emission usually implies a denser region, such as a galaxy's interstellar medium, a star-forming region, or a shock-compressed filament. If emission is detected and placed at the void distance, the microscale question is what density and temperature are implied, and whether such conditions are plausible without a large gravitational well. A star-forming region provides a plausible setting, because gas density can be high locally, even in an underdense large-scale environment. A shock in a filament can also compress gas locally. If neither is present, the emission claim becomes harder to support. If the detection involves radiosynchrotron emission, microscale mechanisms include particle acceleration, magnetic field interaction, and radiative losses. Synchrotron emission occurs when relativistic electrons, meaning electrons, moving near the speed of light, spiral around magnetic field lines. The emission spectrum depends on the distribution of electron energies and the magnetic field strength. Electron energies change over time due to synchrotron losses and due to inverse Compton scattering, where electrons transfer energy to background photons, including cosmic microwave background photons. In low-density environments like voids, inverse Compton losses can be especially important because the cosmic microwave background is everywhere and does not depend on local density. This means that high-energy electrons lose energy even in a void. Therefore, extended synchrotron emission requires either ongoing acceleration of electrons or a recent injection. Ongoing acceleration can occur at shocks such as those produced by jets from active galaxies, or by structure formation along filaments. Recent injection can occur if a jet episode happened within a timescale short compared to electron cooling. The microscale physics therefore constrains the age and origin of radio features. if a diffuse radio structure is claimed inside the Boötes Void, and if it is not obviously tied to a current active galaxy, microscale considerations suggest it may be hard for the emission to persist unless conditions support reacceleration, or unless the magnetic field and electron energies fall within a range that prolongs visibility. These constraints can be tested by measuring the radio spectrum at multiple frequencies and by searching for polarization. If the detection involves X-rays, microscale mechanisms include thermal Bremsstrahlung, meaning radiation from electrons decelerating in the electric fields of ions, and line emission from highly ionized atoms. Thermal X-ray emission implies hot gas with high temperature. The brightness depends on density squared, making it difficult to detect from diffuse void gas. Therefore, a microscale interpretation of X-ray emission usually points to hot gas in a galaxy group, a cluster, or an active nucleus. An active nucleus produces X-rays through processes near the black hole, including hot corona emission, where high-energy electrons scatter lower-energy photons to X-ray energies. This is a compact source. If the X-ray detection is extended, hot gas becomes more likely. If it is compact, an active nucleus becomes more likely. In either case, microscale physics relates observed spectrum to temperature, or to emission processes, allowing estimates that can be checked for plausibility in a void environment. If the detection is a faint galaxy within the void, microscale mechanisms include star formation regulation and gas stability. Star formation requires gas to become dense and cold enough to fragment. In small galaxies, gas can be kept warm by the ultraviolet background and by internal feedback. Supernovae can stir gas and drive outflows. In a void, the external pressure is low, which can make it easier for feedback to expel gas. Yet low interaction rates can allow gas disks to remain stable and undisturbed. Star formation can then proceed slowly. The microscale of this process involves cooling by metal lines dust shielding that allows molecules to form and turbulence. These details shape whether a galaxy is bright or faint, compact or diffuse. They can explain why some void galaxies have large amounts of gas but low star formation rates. Therefore, a detection of an unexpected galaxy type inside a void can sometimes be explained by microscale balance rather than by large-scale contradiction. Another microscale mechanism relevant to void claims is measurement noise and systematic effects. At the faint limits, detectors produce signals that must be separated from background. Cosmic rays hitting detectors, variations in flat field calibration, and subtle scattered light within instruments can create patterns. These are not physical mechanisms in space, but they are microscale mechanisms in measurement. Because void detections often seek faint signals, such systematics can be decisive. This is why repeated observation and independent instrument confirmation matter. In the inward progression, microscale mechanisms provide a disciplined way to connect signal to cause. They also provide constraints that can rule out certain interpretations without dramatic language. A void can host faint gas, small galaxies, and rare active sources. The microscale physics tells what signatures should accompany each. If those signatures are absent, uncertainty remains. The next and final inward step is to state what the claim would imply if confirmed, what remains uncertain, and why uncertainty can persist, all while staying within the physical bounds established by measurement and by consensus models, and without turning the discussion into meaning-making. The innermost layer of the topic is the claim itself reduced to its strongest form and separated from its weakest interpretations. Something is detected inside the Boötes Void. If the detection is confirmed and placed securely within the void interior, it becomes a statement about what kinds of matter and activity can exist in a strongly underdense region. It does not become a statement that physics fails. A void is not a prohibition. It is a statistical environment. The innermost approach therefore states what is physically plausible, what would be genuinely unusual, and what remains uncertain even after careful work. At this level, the key is restraint. The aim is to describe what the evidence can support and to describe why some uncertainties persist, because the environment and the methods both impose limits. If the detection is a compact object with a secure spectroscopic redshift within the void and far from the boundary under multiple void definitions, the most direct interpretation is that the void interior contains at least one luminous system beyond what a simplified picture suggests. This could be a faint or ordinary galaxy that was missed in earlier catalogues. It could be a gas-rich dwarf galaxy revealed by radio surveys. It could be an active galaxy whose emission makes it stand out. None of these violates consensus models. Voids contain some galaxies. The density is lower, not zero. The unusualness would be in the rarity, not in the mechanism. A large void volume can still contain rare objects. If the claim is framed as making no sense, one innermost correction is that sense must be measured against probability. The question becomes whether the object's properties such as luminosity, mass, or activity are consistent with a galaxy that can form in a low-density environment. For many properties, the answer can be yes. The environment shifts typical distributions but does not forbid outliers. If the detection is not a compact object but a diffuse signal placed at the void distance, the innermost interpretation becomes more delicate. Diffuse signals are harder to place in distance and easier to confuse with foreground and background contributions. If such a signal is confirmed across instruments and wavelengths, and tied to the void distance through spectral lines or through association with a void galaxy, then it becomes evidence of physical processes acting on scales larger than a single small galaxy within an underdense environment. For example, it could indicate a large radiolobe system in a low-density medium where lobes expand farther and remain detectable under certain conditions. It could indicate a faint filament of warm gas that becomes visible through absorption or weak emission. It could indicate a subtle mass structure inferred from lensing. These interpretations remain within known physics, but they would refine understanding of how structure and energetic processes extend into void interiors. The genuinely unusual case would be a detection that implies a deep gravitational potential, well, such as a massive cluster-scale structure located securely within the void interior with supporting evidence from multiple independent mass tracers. That would challenge the expectation that such large wells are rare in strongly underdense regions. Yet even that would not require new physics as a first response. It would require a re-examination of how the void is defined, and of whether the region is truly as underdense in mass as it is in bright galaxy tracers. It could also indicate that the void contains significant substructure, and that the boundary between void and filament is more complex than represented by coarse mapping. Another genuinely unusual case would be a widespread diffuse emission that implies high density or high temperature gas filling a large fraction of the void interior, because the low density environment makes such conditions difficult to sustain without a large source of heating and confinement. If such a claim was supported, it would imply either hidden mass structures and incorrect distance assignment, or a need to revise models of gas heating and distribution in voids. In practice, such claims are hard to support because emission is suppressed at low density, and because systematics become severe at faint levels. Therefore, the innermost layer emphasizes that the strongest surprises are those that survive distance checks, multi-wavelength confirmation, and mass consistency tests. Uncertainty remains a central feature of this topic for several reasons. One reason is sampling. A void is large, but observations sample it unevenly. Galaxy surveys have limits. Absorption studies sample only narrow lines of sight. Weak lensing requires many background sources and is noisy in low-density regions. Therefore, even after many observations, the interior can remain incompletely mapped. Another reason is definition. The void's boundaries and interior depend on tracer choice and threshold. Different surveys and algorithms yield different shapes. This means that the statement inside the void is not a simple Boolean. It is a statement with dependence on method. This can be reduced by using multiple definitions and by focusing on objects well within the interior under all reasonable definitions, but it cannot be eliminated entirely. A third reason is line of sight confusion. Even with redshifts, some signals do not carry distance cleanly. Diffuse emission can overlap in projection. Foregrounds can be structured and faint. Instrument systematics can mimic low-level patterns. This is why some uncertainties persist even when the data are extensive. At this innermost stage, the most disciplined result is a set of constrained implications. If the detection is a galaxy or a small group inside the void, it implies that void interiors host more low luminosity structure than shallow surveys reveal, and that isolated evolution can produce a range of galaxy properties including rare activity. If the detection is enriched gas in absorption, it implies that metals can reach into underdense regions, likely through outflows and long-term mixing, and that the void intergalactic medium is not chemically pristine everywhere. If the detection is a radio structure tied to a void galaxy, it implies that particle acceleration and magnetic fields can produce detectable synchrotron emission, even in low-density environments with microscale constraints on age and energy injection. If the detection is a mass anomaly inferred from lensing, it implies that void mass distributions may include more substructure or that tracer bias must be accounted for. Each implication is a refinement rather than a rupture. What remains uncertain is the full distribution of faint galaxies, the detailed state of void gas, the strength and coherence of intergalactic magnetic fields in void interiors, and the degree to which rare energetic systems occur in such environments relative to their occurrence elsewhere. These uncertainties are bounded by ongoing measurement. They do not license speculation. They are simply the edges of what current data can resolve. After this innermost layer, the script moves into the wind down, maintaining the same calm, neutral tone and constraints, allowing the details to settle without adding conclusions or meaning-making.